Hello, I welcome all of you in this video. This video is regarding one of the continuous distribution type, that is normal distribution. First of all, I'm going to tell you that my whole this lecture of normal distribution has been divided into three videos. In the first video, I will tell you that what is the normal distribution graphically, differences mean, differences in variation among the normal distribution depending upon different type of data. Then this video will include that how we can calculate the areas under the curve by using the formulas, by using the given z values. So this will be my whole video. In the second video, we will solve few examples that are related to normal distribution, and the third part of the video it will be consist of purely engineering or applied videos that are related to the normal distribution. So first option, it is also known as Gaussian distribution. It is a bell-shaped distribution with a mean at the center of the curve. Okay, the density function of the normal distribution is represented by this. Further, most important thing, that the mean, mode and median, you can say mean, mode and median of this distribution lies at the center. Okay, so all this is basically a symmetrical distribution, that data at half at the one side of the mean is equal to data at another side of the mean. Means the data at the one side of the mean is equal to data at another side of the mean. So this is normally distributed. Okay, now as objective of this video is to tell you that what is these graphs showing us. So these graphs showing us that there are two populations. Okay, another thing, we have to always calculate in case of normal distribution, we have to calculate from the left hand side, as over digits also starting from the left hand side. 1 2 3 4 5 values are always on the left hand side and the higher values are on the right hand side. So what this figure depicts, this figure depicts that we have two populations. This is population 1 and this is population 2. Fine. Now it shows that both of the figure have both of the curve have are same. So it means that they have same variance. Okay, same variance, and variance represented by sigma square. Further, these two figures shows that the mean of the population 2 is greater than mean of the population 1. How we can infer this decision? It is quite obvious that the mu2, mean of the second population, lies towards the right hand side as compared to the mean of first population, that is represented by mu1. So it will be quite obvious to you people now that how we can interpret the graphs. Further, this is the second graph. Again, the steep one curve, it is population 1, you can say it, and this is less steeper, flattic. Okay, and the another one is leptokurtic. Okay, the population 1 is leptokurtic. This is population, sorry, this is population 2. Population 2. So what we will what will be the over inference over decisions using these two graphs? So we will say that the distance from the center point till the end of this curve, or from this point to this point from the center, it is quite less as compared to distance from the center to the maximum point of the curve of the population 2. So it means that variance 1 that is related to the population 1 is less than standard deviation, or is the variance of the first population is less than variance of the second population. Okay, but then again, what about mean? The central line of both population 1 and population 2, that lies on the same point. So the mean of both populations are same. So it is obvious to you people that if the mean of both two populations are same, then their variances can differ. This is the second case. Then again we have two samples or population, you can say. We represent sigma 1 by, and we can say it's the data of the population 1, population 2, or you can say sample 2. So what is it meant? It is from the last two slides. Now you people are quite familiar with the decision. What first decision will be that mu2, the mean of the second sample lies towards the right hand side as compared to the mu1. So we can take first our decision or inference that mu1, mean of the sample 1, is less than mean of the sample 2. Then what will be your second decision or second inference? We say that, okay, now again you will check that how we will check the variance. We will check the distance. You will check the distance from the central line to the outer point of the curve. Okay, which one distance is smaller as compared if we compare both of the curves. So you see that in case of population 1, that is leptokurtic, the distance is smaller as compared to the another, you can standard deviation, and this standard deviation is larger. So greater the distance, greater will be the larger or greater will be the standard deviation. So you can say that mu2 standard deviation of the second sample is greater than standard deviation of the first sample. Again, you can say that the variability of the second sample is greater than as compared to variability of the first sample. The mean and variance of n is the sample size. Okay, so mean is represented by mu and variance is represented by sigma square. Okay, division is represented by sigma. So this notation is for sigma. Now we will calculate areas under the normal curve. So in order to calculate, first of all, the basic concept would be that the area under this whole curve is equal to 1. You have studied in the FSC. Fine. Then how we will calculate the area? We will just have to take the definite integral. This is basically if you got integration sign and there are no limits upper and lower, no interval has been given, so you can say it's a indefinite integral. Indefinite integration you have studied about. Okay, so but if I say that integrate and I set the integrate between these two intervals, so we got the area under the curve between the stated interval and we say this is definite integral. Okay, and the result will be the area under the curve. So now normal distribution of a random variable, the mean is always 0 and variance is 1, standard normal distribution. So again, if someone tell us that let's suppose this is your sample and sample have mean mu, standard deviation of sigma, you will have to calculate the area between these 2 points. Let x1 and x2 be the two points. So first of all, what we will have to do, we will have to convert these points into z-scores. What are now z-scores? Z-scores are normalized values. You can say that the x1, x2, these values may be too much large for one data, may be too much smaller if we are calculating another smaller value. So there will be problem for us to use the standardized normal distribution tables. So first of all, what we will do, we will calculate the standard normal values that are associated with specific points or specific values of our data. Okay, so the formula for calculating the z values is very simple. You have to subtract the observed values. You can say x1 minus mean of the data mu divided by sigma. That's very simple formula to calculate the z scores. Okay, so in this second figure, it is telling that you have to calculate the area between z1 and z2. So first of all, what we will do, by the concept, we will always, I have told you that always take the calculation. You will have, it is obligatory that you will take the calculations from the left hand side. So first of all, you will take the you will calculate the probability that is associated with this z value. Okay, you will calculate the probability associated with this z1 value from the left hand side, and you can say it's my area a1. I will write here a1. Then you will calculate again the probability value associated with this z2. Okay, from again from the left hand side, and this left hand side, it will give you a second area. You can set area 2. Now what you will, if you have to find the area, you will say subtract a1 from a2, because we have a1 as a1 as the area from the left hand side till z2. Okay, and we have area of a1 from the left hand side till z1. So it is obvious to you people from the, you can say, figure, that we are only interested area between the z1 and z2, and we do not interested with this white color area. What we will do, we will calculate the whole and we will subtract this white color area that is emitted by a1 from the a2, and we will get over this shaded region that has been blue colored. So this is the way that how we will calculate the probability under the curve associated with a specific area. So this is an example. In this example, it has been inquired that calculate the probability associated with this area that has been blue shaded. So first of all, I have told you that start from the left hand side, from this side. So what we will do, we know that area under the curve is equal to 1. Clue is that area under the curve is equal to 1. So we say that the area between 2 points, it will be represented by a1 and it is equal to 1. The second thing, we know that the area from the left hand side till this point, we say this is equal to a2. How we'll calculate this area? We will calculate by using the standardized normal table, and we'll find the value of the probability associated with this z is equal to 1.84 in the table. I will tell you about that, how we will calculate the values that are associated with a specific z value using the table. But we are interested in this area, and this area, we say this area is equal to a3. So how we will calculate a3? We say that a3, this will be equal to a1 and minus a2. How? a1 is the whole probability associated with the whole this range, area under the curve, and this is equal to 1 minus a2. a2 is the area that is associated with this white region, So if we calculate the probability associated with this white region, okay, with the probability from the left hand side till the point 1.84, and we subtract it from the 1, we will get this value, the probability that is with the a3, with this area that has been shaded with the blue color. So I am going towards the you can see z distribution table in order to calculate the probability value that is associated with a2, that is with the 1.84. So I will get a probability value for a2. I have opened the table A3 in your book. The heading of the table is areas under the normal curve. So in the presentation, we have z value is equal to 1.8. Slide, this is equal to 1.84. So in the table, we will look at the probability associated with the z value 1.84. So first of all, what you will do, you will check this column, okay, z column in the vertical downward direction, and you will see this is 1.8, but you need 1.84. So the rest of 0.04 you will check with this horizontal column at the top of the table, 0.04. So in the intersection, on the intersection of these two values, we got 0.9671. So this is the way that how you can calculate the probability associated with the specific z value. So from the table, we have got that the value is 0.9671. We will subtract this value from 1 and we got 0.0329. So this is the way we have calculated that the probability that we got a value that have z score is equal to 1.84. The probability is 0.0329. So this was the method that how we can calculate. Now we will go towards the next example. The next example say that calculate the value between the two z score are given. The one of the z score is z1 is equal to minus 1.97, and z2, this is equal to 0.86. So first of all, go directly to the z distribution table and calculate the area a1. So area a1 will be equal to, from this point to this point. Okay, and then calculate the area A2 that is associated with the z value 2. You will say that it is z value 1, z value 2. Okay, so what you will have to do, you will have to calculate that the probability that is associated with the area A1, the probability that is associated with the area A2. Just subtract A2, the probability associated with the A2 from the probability associated with the A1, and probability that minus 1.97, it will be greater than z value, and z value is greater than minus 1.97, but it will be less than 0.86. Okay, one more thing for you people, that the positive z values are always on towards the right hand side from this center value, and the negative z values are always on the left hand side from this mean value. This is over mu. So what you will do, we will calculate the probability associated with 0.86 and minus 1.97. Again, we will go towards the z distribution table. So how we will calculate 0.86? Again, come towards vertically downward. This is 0.8, and you can say this is 0.06. Again, at the intersection of these two values, you can say this is from the x-axis, and we got this value in the y-axis. So 0.8051 is the probability associated with this value. Now the question is that how we can calculate the values for the negative so this is another table. This is table A3, areas under the curve, but here the z scores are negative. What's the score we have to calculate? We have to calculate minus 1.97. So minus 1.9, we will again come towards from the top till downward, minus 1.9, so 0.07 remaining. Look at the x-axis. So at the intersection or at the junction of these two values, we got the probability that has been associated with this minus 1.97. We will move towards our so we will write here that probability that has been associated with z less than 0.86 minus the probability that has been associated with z greater than minus 1.97. We will just subtract these two probabilities, and we got 0.8051 minus 0.0244, and this will be equal to 0.7807. So these were the few methods that how we can calculate the areas under the curve. In the second video, I will cover the remaining lecture. We will solve one or two more examples like this, and then I will go towards the question that related with the with some statements. If you're new to my channel, please subscribe. If you have any questions, you can do comments. Thanks a lot for watching this video. Bye bye.